The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our first speaker is Poole, and he is a chemist and biologist by education. Came to concrete by way of job requirements for Corps of Engineers. Worked for the Corps of Engineers in Vicksburg for 30 years. He's retired, but although he's very active, and he's working as a part-time in CTL. And he will talk about the issues, specification, what we got, and what we're still expecting. Welcome, Toy.
Thank you. Yeah, it was because of marrying that I had to abandon biology and become a concrete guy. The fact that my formal education doesn't have anything to do with what I claim to know how to do. It's something I was in a legal case with the Corps of Engineers right before I retired. The attorneys for the other side had some fun with that issue. I had no formal education in what I thought I knew something about. They were kind, though. There I am, a couple of years ago. I don't look too much different. Well, one of the things I want to say right off is there's been a lot of work done over the years, and last 10, 15 years in big research programs, and these things have done a wonderful job of creating some new tests, of adopting some, and modifying some test methods and specifications and approaches. And I can't think of anything bad to say about it. So I'm not here to, get on the case of that, the concrete specifications that we're putting together right now. I think they're a good thing. But the purpose of this talk is to kind of give you a perspective from a technical representative standpoint for a major public, Corps of Engineers. And there we worried a lot about things when we were building things. We're building very expensive structures that people like to last a long time. Typically the service life was nominally 50 years, but we have things out there that are 75 years old and things like that. So when we build things, we worry a lot about things way down in the details. And that's kind of a habit I got to when I was working there. It's gotten to be kind of a hobby with me now. I like to look at things, the methods and the specifications, and try to determine where they came from, and what they're doing and what they maybe aren't doing that we think they're doing, and this kind of thing. So what I'm doing today is there are a handful of these that bounce around our current practices that I think are kind of interesting. They may or may not be all that important, but some of them might be. So I'll go through some of those. Just a little bit of background. I think it's right. Jim Pierce is back there, and he's quite a bit older than I am, so he might have a little more perspective. These structures I'm listed over here are mostly probably Bureau of Reclamation structures. But a lot of public works in the 1920s and 30s, and a lot of that turned out to have some kind of alkali-aggregate reaction, and also some transportation structures in those days. And people didn't understand it. And, as most of you who know about this subject know, that Stanton published the first work on this in, I think, about 1940. And it was very quickly thereafter that they identified alkalis in cement as a major feature. And you'll find, if you look around the older literature, you'll find these kinds of graphs around that show alkali content in cement and expansion. And interestingly, they all have sort of the same quality. It shows no expansion essentially up to about 4/10 alkali. Then they have a fairly steep ramp up to about 8/10 alkali. Then they kind of bend over. And a lot of them show this sort of very high alkali decline. Nobody ever makes anything out of that. I first saw, well, given the size of the error bars, maybe that's just random error, but I've seen it on several other sets of data too, and I don't know if we need to make it. It's very rare for cement to have alkali contents higher than 1.2%, but it's kind of a curiosity. But fairly quickly, the alkali content of cement became the major feature in alkali silica, in the concept of mitigating alkali silica. We had some test methods in those days that you recognize if you work in this area because they're still there. The quick chemical method, the mortar-bar method, and the mortar-bar method modified for use with pyrex glass.
In the 1980s, we used that guidance, low alkali cement. I remember when I first came to work for the Corps in 1980, and for a number of years thereafter, the rule was if you have low alkali cement, you don't worry about anything. You're covered. There's nothing else to do. And we built a lot of structures that way. But looking in the older literature, people knew in the 1940s that pozzolans helped a lot. They also knew, as I showed in that graph, that low alkali cement wasn't always the answer. There's that business right in here. And we knew that. We just didn't implement it really. We just sort of saw the bigger part of this graph and went off and built the guidance around that. And we paid some prices for that. I know the Corps' got some structures that are not doing too well these days that were built with that low alkali cement concept is the only variable. So in the 1980s, improved test methods were developed. The now somewhat famous 1260 and 1293 and 1567 were all developed, I think, in the late 80s, and they were standardized in ASTM in the 90s and early 2000s. I think they're in the Canadian literature a little early, guidance a little earlier than that. We've had field service records around for a long time, and they've normally been held to be the gold standard, and I'll talk about that in a minute. And now we are really moving along. We're developing a comprehensive concrete specification. One's already been put into the AASHTO literature through some federal highway work. And ASTM is working on a similar document. Our friend Jason Eidecker is sitting down here, and he's chairing the group in ASTM that's working on that. And these things contain a lot of information and are really nice documents that are coming along. And what maybe is coming new is this whole business. You know, we used low alkali cement as sort of the reference condition for many years. And as I'll say in a minute, but I'll say it now and then say it again in a minute, right now we think that the concrete prism test, the 1293 test, is sort of our reference condition. And nowadays people are doing things like taking big chunks of concrete and putting them in the outside. We've got some in Central Texas. The University of Texas has one, and I know Texas DOT is starting up some of this same kind of work. And there's some in Canada, and I know there's some in England, and there are various around. And this may, in the long run, be very helpful to us. I think it's already giving a lot of good data that'll help us to maybe make some progress on some things that we have been either ignorant of or confused about. Here's where I think one of the problems is that if you read all the information that's been developed in the last few years, you'll see quite a lot of detail and quite a lot of understanding there. In practice, however, it's rather common to just sort of ignore all of that and to run a 1260 test. If it doesn't do well, throw some fly ash or slag in and run the 1567, and if it meets the limit, you go. Many people just skip, and so we skip what we consider the standard condition, which is the 1293, mostly just skip around that. And in fact, sometimes we skip that one too, and we just go straight here. And that tends to be, in many applications, that tends to be the approach. And so the alkalis have been de-emphasized. We mostly rely on supplemental cementing materials, and these are more or less, people differ a little bit in how they use it. There's less than a tenth or less than or equal to a tenth, some differences there. The military has gone off on a wild tear and reduced this to 0.08% at 28 days, and this one is less than, in other words, less than or equal to 0.03, but that's kind of a detail, which is a significant detail in an economic sense. But I'm probably not going to talk about that today, but I can if we want to do that. Alkali-carbonate reaction has been a little bit of a neglected child, and that's because it's not as abundant, as common as alkali-silica reaction. It's identified in the 50s and 60s, and a couple of test methods have been put together, and there's been sporadic work on the mechanism over the years. And lately there seems to be a little bit more of a renewed interest. This one has caused the Corps of Engineers quite a bit of problem in recent years. And I may end up talking about that a little bit, but I think down later on I've got a slide on that. Some things I think that we don't get. Let me talk about field service record first. C-33 has in the appendix, has a discussion on field service records, and it's about 10 years at least, and that the materials are the same and the conditions are the same. And people quite often, I know when I hear people talking about whether we should do this or that and the way they're developing specifications and test methods, they tend to say, oh, what's it doing in the field? What's it doing in the field? That's always what they want to throw up the reference condition. And the problem is that it's very rare that we can really use field service records. The conditions are variable always. The materials tend to be variable. Cements tend to not be quite what they were yesterday, maybe not even the same source of cement. Age is sometimes a problem. And the biggest problem is lack of records, really. So often we run into structures, we run into them all the time that are going bad. Something went wrong when they put it together, and nobody has any records on it. And so in practice, this one, even though it sounds like the one we ought to be relying on, in fact, very rarely do we rely on it. So I always kind of when we get in a group like this and somebody says, well, what does the field record say? And if this is a good idea, it should show up in the field record, but there is no field record really. Now, I think there may be more information out there than we know about, but it will take some work to find it, and I don't think we have that right now. So that's one of the things that our guidance, and it cites, the newer guidance cites field records quite a bit, and not quite a bit, but it cites field records. And I'm not sure how useful that is to us, and so leaning on that might be a bad idea. What I think is kind of a big hole in the current guidance, things that it's not telling us, is about blended cements, and I don't even know about C1157 cements. These are cements that are made, they're non-Portland typically. They oftentimes are Portland cement with blending things in them that don't qualify them to be a C595 cement. And they may not even be Portland cement. They may be some other mineralogy altogether. And our methods now are mostly performance methods, and they don't really have a niche in them for these kinds of materials. Lithium is the same way. There's no real method out there. Now, we're pretty close on lithium. I think we can use 1157 and doctor that up and probably have a method with that. And specialty cement, some of the repair materials and things like that. We don't really have a performance way, I don't think, of looking at those. Because most of our performance tests are put something in sodium hydroxide, which fouls up whatever chemistry is in these things. It masks as something fierce, and so it's really hard to work with. We conceivably could do a concrete test with these. You can always do a concrete test, but of course that's a year long, and so that's turning out to be a very difficult thing in practice. Finding people that really will do concrete tests because of the length of time for that. So that's a place that I think we need to do something. I don't know what, but I'm just a critic. Well, there's that thing: if you can, you do, and if you can't, you criticize or talk about it. And that's me. So and the other thing that's gone wrong is where we used to rely on cement content, Portland cement content, low alkali. It was probably correct to go away from that as a central guiding feature, but the methods now are not, don't tell us anything about the alkali content of the cement, what contribution that might make to the overall pattern. The whole system is set up as it's based on a high alkali reference condition. And it says whether something can correct for high alkali cement situation or not. And that makes a certain amount of sense. The logic is that if it can correct for a high alkali cement condition, then it should be able to take care of anything. And I'm not criticizing that logic. What we're finding, though, is that there are people in places that would like to, if low alkali cement is a benefit to them, like there are places in Alaska, for example, that getting fly ash there is not very easy. Hawaii is another one that for a while didn't have access to good pozzolans. And they, for the longest time, have been using low alkali cement and relying on it, and they thought they were probably doing okay. But then they found the aggregates were reactive, and then there was some question about whether the low alkali cement really was doing the job in the long run or not, kind of thing. So we don't have any way of really evaluating that. So The alkali content of cements has kind of fallen out of the mix a little bit. We have alkali loading concepts, which to some degree will cover up for this, but they're based only on the cement alkalis, and these alkalis of the supplemental cementing materials, we have some information on that, and the new specs do set numbers out there, like 5% or 1% alkalis in them. But I don't think these are particularly well-developed numbers with a traceable path to them and that kind of thing. So I think we've got a little bit of a problem there, and in working with what is the central feature of ASR, which is the alkali content of the cementitious materials. There was a little bit of a glitch there for some materials. For others, it's fine. I think we're doing fine. Plain old Portland cement with supplemental cementing materials is, we're doing fine on that. This one is just kind of a arcane situation. I call it alkali redistribution. The whole business of when you build a structure up against a moisture, like a retaining wall, or in this case a light post thing, and you have groundwater that can move through that and then evaporate out the other side. Alkalis, being as soluble as they are, will move with them. And it's kind of something in lore that you hear about, I've heard about for decades now, that you can redistribute the alkalis when you do that. So you get high alkalis in the surface at the expense of lower down. Now this is probably not alkali silver, that's probably some sort of a physical salt attack, but sodium sulfate is, it's a soluble salt, and this is some work that we did in Vicksburg, where we were out at Holloman Air Force Base. We had a pavement, and the cracking pattern in the course looked like it was more towards the top, and the orientation and all that made me wonder. So I went and looked at the alkali content, and sure enough, in the top 50 millimeters, it was quite a bit higher than it was down here. And then we had a patching material that was up in the joint patch, and its alkali contents were way up here. And there was what appeared to be some bleeding over of ASR into the neighboring concrete. Now we were just bootlegging this work, so we didn't really go very far with it. So I don't think I've proved anything there, but it's something that we don't think much about, well, will alkalis move around in a structure and concentrate in certain points? This is one that I've come upon recently that's kind of interesting to me. It really has to do with temperatures. We've known for a long time, of course, that alkali-aggregate reaction is accelerated with temperature, was the basis of our accelerated methods. And I'd always thought that the degree of the difference between two terrestrial environments would not be such a big enough temperature difference that it would be something that would show up in our work. And what we seem to be seeing here, if you look at these, for example, the green one is one that is an outdoor block in Texas, and this is an outdoor block in Canada. I'm sorry, it's the other way around. Texas and Canada. Yellow, red. And this is in pretty early stages. I don't know how, this may turn out not to be anything, but it's looking like from this that there may be something to this, that there may be, when you've got a place that averages close to 20 degrees C and another place that maybe averages closer to 10 degrees C. But that's enough of a difference that over a relatively long time period, that might actually have a significant effect on the rate of some reactions. And squeezing a little more information out of this, some of them appear to have a big difference, like this green one, which was the Sudbury aggregate. Was not really expanding much in Ottawa, and it was expanding well beyond any generally accepted criterion in Texas. So there might be something there. This is not something that's in our guide of anything we worry about. It's something that came up back in the 1950s. The whole business of activation energies and Arrhenius work and all that came up in the 50s and sort of passed on by as other things washed over it, and it may be coming back now. So the question is, do different aggregates act differently in different temperature environments? Some maybe have different activation energies than others. That wouldn't be too surprising. Long-term projections, this is a big problem I think we have. We don't really know very much about, if somebody says I want a 50-year service life. For the longest time I thought that when we did an accelerated test method, this basically got all of the reaction out of the mix we were looking at. And if it didn't exceed a cracking threshold or something at that point, then we were home free for whatever reasonable service life you might want to get. Well, if you play around with this Arrhenius concept a little bit and dig around the literature for some Arrhenius values, there's not much out there, and you plug them into some calculations, you can kind of convince yourself, and I'm not saying this with a great degree of confidence here, but that a 1 year, 38 degrees C test might be good in Canada for maybe as long as 25 years or so. It may be what it's kind of projecting. That might be the translation of 38 degrees in the lab to whatever the temperatures in Canada are. And if that kind of thing is true, then that might be a reasonable assumption that the tests are telling us all we really want to know about the reaction. But if you look in Texas, where the temperatures are quite a bit warmer and use those same activation energies, they're telling us that these test methods aren't translating into field conditions that all that far out. And if that's true, I'm kind of holding, but if it's true, then that's a detail I think might be important. And I think people, I know, and I was working on some of these things, and some other people, I know the guys in tech that have been doing this work that, have got these blocks, and they're the ones that generated the data. It wasn't me. So I know they're interested in this, and so this is things we'll be looking at, I'm sure. So this is the one on alkali-carbonate reaction. It's you'll hear people commonly say that, well, if you want to know if it's alkali-carbonate reaction or not, run let's see 1105. That's a concrete prism test for alkali-carbonate reaction. Well, I'm sure there's nothing unique about that test that selects alkali-carbonate reaction. It was before the ASR test was existing. The people that were doing alkali-carbonate work said, well, let's make a concrete prism test, and they did. And it showed up as useful for their work. And then they just stuck, well, we work on alkali-carbonate reaction, so we'll stick that on the title. And people now take that as an indication of specificity for that. Same with C586. It's long been held that the rock prism test, only reactive dolomites showed positive expansion in the rock prism test. Well, that's not true either. I mean, I can testify to that one because we did a lot of work on the replacement for the Chickamauga lock looking at dolomites that were not alkali, didn't have the alkali-carbonate feature to them. They were expanding happily in this test method. So I'm pretty sure that this specificity that we in the 1260 is specific to ASR there is commonly held that when you crush the aggregate, it won't expand in 12. And that may be true, but I'm not exactly sure. I haven't seen the reference on that. But anyway, so we have those kind of things. Let me get to this one, and then I'll say this is a pet of mine. We test aggregates as fine aggregate, coarse aggregate. We don't usually consider the situation, what if you have both in the same concrete? What's going to happen there? And our test methods don't help us there. They just say, it's just a tough situation, And, so what people have started doing is they've started going off and doing mortar-bar tests where they put half coarse aggregate ground up into a sand, take half or whatever the job proportions are, and make a mortar-bar like this one. So you test the fine aggregate, and then they say, well, it passed, so therefore we should be able to use this as a criteria. The catch here is when you do a fine aggregate that expands 0.1% will translate into, we know this just from correlations, to a concrete prism that has half unreactive and half the reactive sand of about that percent. And that's what the limits are we use. Coarse aggregate the same way. If you do this, and this is the practice that people are doing, then the analog would be to go over and do the concrete prism test like this. So now we don't have half the aggregate is unreactive. We have it all is reactive. Is it reasonable to think that expansion would still be 0.04? Or would it be double? Or maybe it would be less. I mean, I think aggregate interactions might be funny things. And I'm pretty sure we don't know much about that, don't understand much about that. But to just run off and do this and say, oh, it didn't expand beyond this didn't expand beyond 0.10, I think is ignoring a lot. So I think that might be a practice that we've tried to put the clamps on it, but people just do it anyway. So that's one. And let me stop. One of the things I really would like to do is to spend more time figuring out what we've got in the ground and what went into it. And if I had a way of getting information, I would like to get, serious history. I know we've got some. I heard some on some nuclear reactors the other day that had some ASR problems. I bet you they've got all the as-built on that. And we've got the thing now. Now, whether they would release those as-built, I'm pretty sure they probably wouldn't just because of the public issues associated with, I know there's one plant that's being considered for relicensing, and there's a big issue of the ASR. So anyway, I'll stop. Sorry to run too long.
Thank you, Toy.